Morning, Janae.
Hi, Alexa.
How are you?
I'm okay. I'm just a little bit tired.
Girl, me too.
Not a little bit, just a lot. What time are you and Azriel having the study session again? Because I probably will be joining because I didn't supposed to do yesterday.
It'll be like at 12 and onward in there, like right after class.
12 and onward. Okay.
And it'll be the same code for what we use to meet as a team.
Oh, okay, great.
So whenever you log on, because you know we'll be talking our stuff when we're ready.
Mm-hmm.
So
Good morning.
Good morning.
morning.
Hey, good morning, everyone.
Good morning.
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 All right, just turned 11. So get that daily quiz going for today. So for your response, for a t-test, when can we use or when is it appropriate to use a directional alternative hypothesis? For a t-test, when can we use or when is it appropriate to use a directional alternative hypothesis? Give you just 2 minutes to type your answers in. That also gives me 2 minutes to switch from my squeaky chair to the non-squeaky chair. All right, just 1 more minute. I'll tell you right now, there's 2 things I'm only looking for at least one of the 2. That might help you out a little bit. Just give me one of the 2.
What do we do if we don't know which one of the two?
No, I'm saying there's 2 things. I need at least one of the 2.
Okay.
It's not an either or. All right. I'll give you 15 seconds just to finish typing. It's already 11:02. Michael, Jareem, thank you for having your cameras on. Ooh, cake. And Ollivander's One Shop, looks like. All right, gonna lock answers here in 5, 4, 3, 2, and 1. Locking answers now. All right. So when is it appropriate to use an alternative hypothesis for a t-test?
But it's when you want to like look at a single end of a distribution instead of both ends.
So yes, that is what an alternative hypothesis is, but that's not determining whether or not it is appropriate to use it. So this little block of text, which was kind of like the big rule, the big watch out whenever you want to do this, is what we talked about on, or one of the last things we talked about on Wednesday, which was it's only legitimate to do it if you have formulated your alternative hypothesis before you started looking at the data, right? The second part is that, as long as there is no scientific interest in results that deviate from that alternative hypothesis. Let me read my phone, forgot to do that. So I was looking for one of those 2 pieces. Mainly, the one you want to worry about the most is that no ex post facto rationales, i.e. you're not formulating it after you see the data, okay? Because there is noise in the data. There could be confounding variables in there. You don't want to let the data lead you. You want to be testing the data, right? So if you have questions for me, now is the perfect time to ask. Otherwise, give me a thumbs up so I know I can move on. Cool. resizing my screen a little bit so I can see both you and iPad. There we go. All right, so today, so we're just going to do a couple examples of doing this formulation, right? So in each of these, we're going to have sample 1, sample 2. Sample 1 is going to be coming from the first population. And second sample is going to be coming from population 2. Okay. So we just want to first go through the process of conducting this t-test. And as Janae was talking about, really the only difference that happens compared to a non-directional t-test or a two-tailed t-test is I only consider a p-value from one tail of my t-distribution, not both. Right? That was the difference between, that's why we have to be careful, because whenever we do a directional hypothesis, alternative hypothesis, we're naturally going to be cutting the p-value in half from when we were doing a non-directional. So we're given this 2 boxes of data just to do 2 different calculations with it. We're going to go with that first box. So we have a sample mean of 10.8 and for the first sample and a sample mean of 10.5 for the second sample. And then we're also given that the standard error for the difference in the population distributions is a 0.23 with 18 degrees of freedom, which means I need to figure out what is my test statistic for all of this sample data. So I'm going to have in the numerator, I'm going to be subtracting 2 terms, then I have a term in the denominator. Let's go with the numerator first. What will I be subtracting in the numerator?
Y bar 1 minus Y bar, the sample mean 1 minus sample mean 2.
So 10.8 minus 10.5, and then someone else, also, by the way, thank you everyone else for also turning on your cameras. I know I didn't mention everyone. But what am I going to divide this by? Oh, I think Michael's saying something, but he's muted. Anyone else though?
SE, the
Standard
different, yeah, the standard error.
Which is what?
The combination of the 2 standard errors from the 2 samples.
Yeah, I was looking for the value that's given in the table, which is a 0.23, but I do like your answer better. So I just need to figure out, okay, what is 10.8 minus 10.5 divided by 0.23? I'm going to get a 0.3 divided by a 0.23. And what is that going to give me? I'll tell you, it'd be whatever 30 over 23 is, that fraction. You can tell me what it's going to be.
1.3043.
3043. So this is my test statistic. Now the other question is, once I have my test statistic, I need to compare this to a t-distribution. How many degrees of freedom am I told to use for these 2 samples?
18.
18. Right here in the box. So I'd be going to figure out what the p-value is for this test statistic, 1.3043 with 18 degrees of freedom. Can y'all hear me? Michael, say something one more time. I thought you were muted before I saw the. No, I can't hear you. Sorry. If you want to leave the Zoom session real quick and join back, I'm about to just show some art screen. So you have a moment. So we're going to go to R. Now R can do, again, a lot of this calculations for us, even including that test statistic. So we take that sample mean of 10.8, sample mean of 10.5, and a standard error of 0.23, 18 degrees of freedom. I'm going to run all of this. Let me clear out some of this other stuff. But I run all of this and we should hopefully get the same test statistic. Yeah, 1.34 1.3043. So then I got to say, okay, well, I know I need to get a single tail, right? Again, we're going for alternative hypothesis. I don't think I explicitly stated it, but it's in the problem. That the first population mean is greater than the second population mean, which means I'm going to be going to my t-distribution. I know that I have a positive test statistic, so I'm somewhere on the right half of that t-distribution. And since I'm looking for population 1 greater than population 2 mean, am I going to be looking for the area to the left of this t-statistic or to the right of this t-statistic?
To the right.
To the right. So let me choose a different color. So that's the area that I'm looking for. And I have to make sure I keep that in mind because this function PT naturally gives me the area underneath the curve to the left of that distribution or of that test statistic under the distribution. So if I want to find that green area, which of those two lines of code should I run? Line 11 or line 12? Yeah, I want to run line 11. So I run line 11 and I see that it reports my p-value is a 10. All right, I just said 10, 0.1043. So let me go back to all of our work. Waiting, and there we go. So with this p-value, what can we conclude?
Nothing.
I wouldn't say nothing. You're not wrong, but I wouldn't say nothing.
There's not enough evidence. Wait.
So think back to our table, right? That gave us, let's see, comparing two means. That was just confidence intervals, t-test, there we go. We definitely are above the cutoff that says we would normally want to report there is no evidence, right? Normally above that cutoff. But for our p-value, get rid of that one. How far above of that cutoff of 0.1 are we?
Not very far.
That's 0.43.
Yeah, that 0.0043, right? So really what we're saying is this is a percentage, this is a probability of 10.43%. And we have a cutoff, a general rule of thumb cutoff that says, hey, if I'm greater than 10% probability, I would usually conclude that there is no evidence. If I am less than 10% probability, I would usually conclude that there's weak evidence. And remembering that this is a spectrum. So if I'm really close to one of these cutoff values, I'm not totally sure which one I'm going to be between. In this case, I'm off by 4 1,000ths. So if you wanted to be really conservative with your conclusions, yes, you could say that there is no evidence for the alternative hypothesis. However, what I would encourage you to do is conclude that there is weak to no evidence. For the alternative hypothesis. Because again, that cutoff of 0.1 is arbitrary, right? It is something that we have concluded over time that usually when we get a p-value of this, there is at least weak evidence. We usually interpret this as weak, but it is a spectrum. there is no big difference between 10.1% and 9.9% probability. So make sure that we always kind of keep in mind this spectrum whenever we get close to those cutoff values. Because am I overstating? Am I saying that there's definitely weak evidence for the alternative hypothesis? No, I'm trying to replicate that spectrum, right? Weak to no evidence. I'm kind of in this little gray area here. So what questions do you got for me? And Michael, if you want to give me a mic check to see if it's working now, you're more than welcome to.
Okay, you should be able to hear me now.
Yeah, I can hear you now. All right, but same thing out there. What questions do you have for me? If not, give me a thumbs up.
I have a, well, it's a clarification.
Yep.
So because it's marginally different, you would say it's in between weak and no evidence?
And that's why I'm trying to give that spectrum in my statement, right? Weak to no evidence. You know, there might be some weak evidence there, or there could just be no evidence at all. Based on this p-value, I'm not really going to be certain. So I would say even a more conservative approach and say I give you both options, right? Now, if we're thinking afterwards, right, if you're trying to do some actionable information with some background based off this p-value, you're probably not going to do anything. You're probably going to take it as no evidence. But from a statistician standpoint, this is how we want to report it. All right. Any other questions? Let's do the other table then. So just a second example going through all of this. Well, I guess I could leave it blue. Give me same alternative hypothesis. We're going to be wanting to find evidence for mu1, so population mean from the first population greater than the mean from the second population. And what we have here is that we have a sample size of 750 coming from the first population, a sample mean of 750 coming from the first population, and a sample mean from the second population of 730. So again, I need to calculate a test statistic from this data. For the test statistic, what will be in the numerator?
750 minus 730.
Minus 730. And then the denominator, I'm dividing by my standard error for the difference in the population distributions or sampling distributions, which is what?
11.
Yeah, they give us that information. 11. So this is going to be 20 divided by 11. And what is that going to give me?
One 1.8.
One.
All good. That's the problem with Zoom sometimes. I guess just one of you go ahead and speak up. 1 point what?
8182.
Thank you. And thank you all three for trying. This is why I prefer usually to be in person, because if you all yell out the same number, it comes out as one single number. And I get to choose who I'm listening to, not Zoom. But, oh well, that's our test statistic. What are our degrees of freedom for these two samples? 180. So that means I'm going to go to that function in R to get my p-value. I'm going to give it a test statistic of 1.8182 with 180 degrees of freedom. And I have to remember, so I don't just draw this in R. My alternative hypothesis is that mu1 is greater than mu2. So my p-value is going to come from the area to the right of that test statistic or the area to the left of that test statistic.
Right.
To the right. But this function, p of t, always just gives me the area to the left, which means I'm going to have to take 1 and subtract the value that the function gives me. So we go to R. We'll come back to this if you're still writing, don't worry. We go to R and we just change up our data. Because one of the great things about scripts is as long as we write with those variables that we create, as long as we just change the values of the variables, we can run the same lines of code and it's going to run the same process. So we had our two sample means of 750 and 730. We had a standard error of 11 and 180 degrees of freedom. We can confirm your calculations for my test statistic, 1.8182. If we round to 4 decimal places. Since I know I'm looking for the area to the right, do 1 minus that PT function, and that's going to give me then that my p-value is 0.0353. So then we go back to our work. And with this p-value, what can we conclude?
That there's moderate evidence for the alternative hypothesis.
Nope, you got it. All right. I'm trying to move up a little bit so we get all of it in there or more of it. So with that example done, what questions do you have for me? And if you got none, please give me a thumbs up. Cool. Oh, Janae, is that a question? Cool, go ahead and ask. Don't worry about raising your hand, you're good.
The question that I had was, what would happen if it was the opposite that we're looking at? Like, if we said mu2 was greater than mu1 is what we wanted to look at.
If we were looking at that with this same sample data, all that would happen is your p-value would be different. So let's come down here. So the area above your test statistic is the probability that mu1 is greater than mu2. And then the area to the left is probability that mu1 is less than mu2. So if I use that same sample data, instead of looking for the area to the right of my test statistic, I'd be looking for the area to the left of my test statistic, which in this case, that p-value would end up being what, 0.965-ish. And with that p-value, what would you conclude?
There is no evidence for the alternative hypothesis.
That mu1 be less than mu2. And that's a lot of, there's definitely no evidence for it, right? Which is what we'd expect, because just looking at these samples, that'd be a very, very rare possibility if the population mean for mu1 was less than the population for mu2, but I get a sample from the first population that is larger than the sample from the second population. But when it comes to p-value, all it does is just, you have to look at a different direction on your t-distribution.
Thank you.
Yeah, my pleasure. Any other questions? All right, so let's go on to this next example. So a study was undertaken to compare the respiratory responses of hypnotized and non-hypnotized subjects to certain instructions. 16 male volunteers were allocated at random to an experimental group to be hypnotized or to a control group. Baseline measurements were taken at the start of the experiment. Now, in analyzing the data, the researchers noticed that the baseline breathing patterns in the two groups were different. This was surprising since all subjects had been treated the same way up to that time. One explanation proposed for this unexpected difference was that the experimental group was more excited in anticipation of the experience of being hypnotized. The following table represents the summary of baseline measurements of total ventilation. So liters of air per minute per square meter of body area. Nice little weird unit, but it makes sense. So with that set up and with all of that in mind, we want to use a t-test to test the hypothesis of no difference, right? And then, so what we're looking for here is my null hypothesis is that there's no difference in the baseline measurements between the experimental and control group. And I want to do a non-directional alternative hypothesis, which means my hypothesis is going to be what? Mu1 is what? Mu2.
It's not.
Greater.
Not equal to. So greater than would be directional, right? I'm providing a direction between the two population means. Non-directional means I don't know what direction this is going to go into, what the difference is. I'm just going to say there is a difference. Okay. So then we're also going to do a t-test to compare a directional for part B. So the null hypothesis is no difference again between the two, but then we want to test the alternative that the experimental conditions produced a larger mean than the control conditions. Which if we're going to let, I guess this is important, mu1 be the experimental and the mu2 be the control. For part B, what is my alternative hypothesis going to be? Mu1, what mu2?
Greater than.
Greater than. Because we're wanting to test against whether the experimental conditions produce a larger mean than the control conditions. And then part C, I'll ask you that question later. We're going to see which one we're going to ask and try to determine which one is more appropriate. Let's do it. So let's work with part A. So we have all this data, and from this data, I need to calculate a few things, right? I need the sample means. So I need the means from the experimental group and the control group. I need the sample sizes, which for both of these is what?
16, right?
So there's 16 participants total, and they were split between experimental and control. So my experimental group has 8, and my control group has 8. And then I'll need to calculate the standard deviation of both of these. And then once I have that, I can calculate the standard error for both of these populations individually. And then I can calculate the standard error for the difference in the sampling distributions. And then once I have that, I can then get the test statistic and degrees of freedom and all that stuff. There's a bunch of calculations here, but I don't have to do these by hand. What can help me do all of this? What you should be doing for your homework. Yeah, use R. So you're going to see here, I went ahead and typed in, I have a vector of all the experimental values. So if you can compare to that PDF, you have that 5.32, the 5.6, 5.74, 6.06, and so on. And then a 4.5, 4.78, 4.79, 4.86, and so on. Once I have all this data typed into R as vectors, which I just called experimental and control, I can use R to calculate the means for both of these, the standard deviations for both of these. Now I could hard set the lengths to be 8 since it's a small value, but I can also let R do the calculation for me with this length function. And then a bunch of this code that you should already have written because
I'm
one
not
we did.
sure if it's just me, but I can't hear you, Dr. Red.
Can't hear me. What about now?
Yeah, I can hear you.
Okay, I don't know why muting and unmuting myself worked, but thank you for telling me. So did you hear anything since I switched to R?
The last thing I heard you say, you described what you did to set up the vector for the experimental and control data.
Cool. So
From
all you
then,
do is,
yeah, I suppose that you're just talking about the function you use to get the means out of both vectors.
yep. So I can just type in the values, remembering to get a vector in R. So say like, here's a list of all these data values. I do a C parentheses and then start listing the data values with commas separating each of those data points. Once I have that typed in, that's the hardest work because all of this code should be stuff that you have from the work that we've done in class or you've redone for some of your homework assignments. So I get the means, I get the standard deviations. I can, like I said, or like I was saying, I can hard set. So I can, instead of doing this length function, which is going to tell me how many entries I have in that vector experimental, I could set it to be 8 if I wanted to, since I know that information already. Or I can just let R do it for me. So let's clear out some of these. If I run all of this, control enter, can see that I get, so the experimental group has a mean of 6. Annotate spotlight so you can see a little better. 6.16875. Control group has a mean of 5.29125, which means that there might actually be a difference. I want to calculate the standard error between the two sampling distributions to get a better idea. And I see that it is a 0.318. Once I have that, I can calculate my test statistic in degrees of freedom. So my test statistic is at 2.7571, which is a pretty large test statistic. And I have a degrees of freedom, which is essentially 14. Not exactly 14, but essentially 14. So I am running a non-directional t-test, which means when I'm going to look for my p-values, I take both the positive of my test statistic, the negative of my test statistic, and I need to look at the area underneath the curve for both of these. Let me write that negative TS. Oops, that's a different color. So I take those two areas and get my p-value for a non-directional, which means I just need to double the output from that PT function because this is a symmetric distribution. The tail on the left-hand side is going to be the same as the tail on the right-hand side. And now this test statistic is positive. So which line of code am I going to run? I'm going to run line 23 or line 25.
Line 23.
Line 23. So I get a p-value of 0.01 0.0154. Actually, it'd be 5.5. Because following that 4 is a 5, which means it rounds up to a 5. Now, just while we're here, I can also calculate the directional. We said we wanted mu1, my alternative hypothesis, was mu1 greater than mu2, which means I just need to take one of these two tails that I had from the test statistic or from the p-value, and which one would I be using, the upper or lower?
Upper.
The upper. Which just means that I can run that same line of code. I just don't want to be multiplying it by a what?
By 2.
Yeah, by the 2. I don't need to be doubling it. So if I just run 1 minus that p-value, I'm going to get, or sorry, 1 minus the p function from R. I'm going to get a p-value of 0.007. What's following that 7? 2. So 7. So we get our test statistic, we have our, let me write it down for R. So the test statistic was 2.5 or 7571. And degrees of freedom was 13.9679. So we're going to go back to PDF. So in both cases, we still have the same test statistic and same degrees of freedom, but we get 2 different p-values. So for part A, where we have a non-directional alternative hypothesis, we get a p-value of 0.0155. So what would we conclude with that p-value?
That there's strong evidence that mu1 and mu2 don't equal each other.
Would it be strong?
Moderate to strong.
Yeah, I would probably say more moderate, but moderate to strong also.
I guess with
Go ahead.
no,
ahead,
I
Mike.
I was just gonna say moderate, but I was having I couldn't remember if it was 0.1 something or the p-value is 0.07. Okay.
All good. So there's moderate to strong evidence that the, what is it, baseline measurements of total ventilation is different between the experimental group and control group. Zoom out a little bit. What about for the directional alternative hypothesis? We got a p-value of 0.0077. What would we conclude there?
That there's strong evidence.
Yep, there is strong evidence for what? That the baseline measurements of total ventilation is what?
Greater in the experimental group.
Sorry, Tyler, I had an airplane going by. Could you repeat that?
Greater in the experimental group than in the control group.
Perfect. Wait, is that an I? It's supposed to be an I there. Yeah. Which means I need to fix it over here as well. So once you have that written down, next question I have for you is, which is more appropriate? The non-directional alternative hypothesis or the directional alternative hypothesis? See, if I turn it, you can probably get all of it in there. It's small, but it's there.
I was gonna say that the directional one would be more appropriate because it's what you're, it's in your hypothesis, like it's what you're trying to show. That's what it
I
seems like.
think the non-directional one is more appropriate.
Yeah, I think it's the non-directional one because aren't we not supposed to look at the data in order to use the directional one?
Yeah. So
And there also shouldn't be any scientific, like, how would I say, any scientific interest in one particular outcome, I think is part of the reason.
yeah, really the scientific interest, because this is baseline before they even went into the experiment,
Yeah,
is that shouldn't be a difference, right?
Yeah, they kind of said that that there was a difference between the experimental and control group was an unexpected result. So that kind of inherently says that there's a particular interest in one outcome over the other.
Well, it's not actually that, it's with the process, right? So again, we can only formulate, and Michael, we're gonna want to recall this, we can only formulate an alternative hypothesis if it is done before we look at the data. Alternative hypothesis can only be formulated when it's looked at the data. If we reread the scenario that we were given, so no faults on short-term memory, but it just says baseline measurements were taken for both groups before the experiment, and then in analyzing the data, the researchers noticed that the baseline breathing patterns. So that alternative hypothesis is being formulated by the data, not the science itself. So the more appropriate one to use would have been the non-directional. Does that make sense, Michael? Cool. Just want to make sure. Does anyone have any questions? Anyone else? All right. So one of the things I'm going to show you after this is one thing that can make your life a little bit easier with R if you have the sample data itself. So all of the observations and how to run t-tests. So really quickly, one last time, any questions on this? If not, please give me a thumbs up. Okay. So if you looked at R here, you probably could have saw, because I couldn't get this down. So if our goal is to run a t-test, R has the ability to do that for us. We don't have to do all these calculations even if we can write a script. So the function, I mentioned it when we talked about t-tests the very first time, is this function t.test. What you need to do is give it the experimental data and the control data. Or if you're doing it for some different example, you need to give it the data from the first group and data from the second group. But notice once I run this one line of code, it's going to give me all of this sample output out here. And notice that it reports everything that we have been calculating. What my test statistic was, a 2.7571, my degrees of freedom, 13.968, and a p-value of 0.1545. And it also tells you how it calculated that p-value from the alternative hypothesis. In just this case, true difference in means is non-zero. That's the same thing as saying mu1 is equal to mu2. And then what else does it give us that we always want to pair with any t-test? I'll get you here in a second. The confidence. Sorry, Annie, I interrupted you. Your 95% confidence interval. That the difference in these two means, what population means, is with 95% confidence is between 0.1947 and 1.5602. And also of importance, the means of our two samples, which was the 6.15, which you can, if you look over here on the right, is the same calculations that we got before. So Janae, what's your question?
The fact that it gives us a 95% confidence interval is great. How would the script be edited to say if we wanted to change it to 90 or 99%?
Great question, because it's also going to be something that helps with alternative hypothesis. So you can go and always look at the help screen and look at the documentation. So you're going to see, I want to find out more about this function t-test. I can either do the question mark t.test in the console window, run that, or type it up here in my search window for the help. Either way, it's going to pop up this screen. It's going to give you information about that t-test function. And you're going to look through and say, okay, what are all the different things that I can give it? Well, X and Y are the two vectors of data values. I can also change up my alternative hypothesis by alternatives equal to either two-sided, less, or greater, depending on what direction I want to go in, or conf.level. So let's say if I wanted to take this and change up that confidence level. We'll see. Move that. I'll change my confidence level to, it should be decimal. We're going to check. So 0.9 or 90%. And notice that It still reports everything else, but now the confidence interval that it reports is a 90% confidence interval. And then if I wanted to run t-test, but I wanted to do a directional alternative hypothesis, greater just means that the sample data from the first population is greater than the sample data from the second population. So the experimental population is greater than the control population. I run this line of code. Notice, same t-value, same degrees of freedom, but then it reports that one directional p-value. And a true difference in means is greater than 0. What that's just saying is mu1 minus mu2 is greater than 0, which if I just added mu2 to both sides, alternative hypothesis that we were talking about, mu1 is greater than mu2. So if we don't have the sample data, we have to do some more of these calculations ourselves, getting the p to get the p-value. But if we have the sample data, like you would for your course projects and some of the homework problems that you have, as long as you just take the time to type in all of that data, R can do a lot of the heavy lifting for you. Okay. So I didn't get to talk about paired t-test today like I wanted to at least start it. But like I said, there is the PDF discussion of it up on Blackboard if you want to go ahead and start getting a head start. Because what is due today? You have two things due today.
The fourth project update.
And what else?
And XYZ.
Homework 9. Yeah.
Yeah, homework 9 XYZ. Okay. So as I said on Wednesday, whenever you're talking about what tests you want to run, all of your sample, all of your data is paired because it's all observations coming from the same person. So make sure that you state that you're going to want to run a t-test, a paired t-test. And on Monday, we'll start breaking down what that is. Okay. But you'll see the overall idea, how you still get your test statistic, how you still get your confidence intervals is the same structure. It's just how you get specific values are going to be slightly different. So with that being said, if you have any questions for me, feel free to stick around and ask. Otherwise, get on out of here and I hope you enjoy your weekend.
Bye-bye.
See ya.
Bye. Have a great weekend.
Have a good weekend.
You too.
Okay, I was gonna ask, I
Mhm.
noticed I did the homework 9 and it seemed like, unless I'm doing this wrong, one question just had like, it asked us 9 questions, but there was like 10 points. I'm missing
Yeah,
one.
it's something with the multi-part
Yeah.
of it. So just submit the answers for all 9 parts, and I'm just gonna have to go through sometime this weekend or Monday and just fix that and adjust it for
Okay.
everyone. I was trying to do it because I noticed that this morning, and I can't find a way in XYZ to restructure the number of points for that problem after people started attempting it.
You might have done something too, because now I have like 0 of 9 of those points, but if I just resubmit,
No.
it goes to like where it was previously.
Oh, okay, good. Okay. I didn't think I did anything.
Yeah, it didn't like
That scared
delete
me
it.
for a moment.
Had to resubmit them basically.
All right.
So that was from, yeah. Okay, yeah.
Yeah, for
Anyway.
mine, I just. I know, man. Continue.
What was that, Malachi? Sorry.
So Michael, you were finished?
Yeah, I'm finished, yeah.
I was just saying for number 6, I had put in the right result, but it didn't give me the point for it. So yeah, part of that works out.
Numbers. Looking at you real quick.
I still have one more question to finish though. The last one. And for the fourth report, we putting in like whatever tests we using, the results from those tests, and like our interpretation based on the test result.
So I'm pretty sure it's just what tests you want to run. Because the point of that is if there were some tests that you wanted to run that I hadn't covered yet, then I would be able to try to fit those into in class. So we could talk to them as a group rather than it has to be something you learn on your own, or I would set up a time to talk with y'all.
Right.
So yeah, just identify, just identify any statistical tests you'll be using and why you chose them.
So I was gonna, would it be appropriate if we did like our two-tailed t-test between the means of the two answers we're comparing, like?
So that's what I was saying. You wouldn't want to do a two-tailed t-test. You're going to want to do a paired t-test.
Paired.
Because
Okay,
both of those questions, both the answers are going to be coming from a same person, right? So those two answers are related. And what you're going to look for is if there is a difference. So that's what we're going to be talking about on Monday. So just use that language, paired t-test.
Okay.
Cool. All right, that's it for me.
Cool.
See you later, gentlemen.
All right. Have a good weekend. Any other questions, Michael, or can I end the meeting? See you.